Hi, everybody. We have another session now with a couple of talks. Starting us off is Bernd Finkbeiner. Bernd is a faculty member at the CISPA Helmholtz Center for Information Security and a computer science professor at Saarland University. He's been leading the reactive systems group there and done a lot of interesting work, in particular on hyperproperties, hyper LTL, which we just heard mentioned. His research focus in general is on development of reliable guarantees for safety and security of computer systems, including specification, programs, verification, synthesis and repair, and both static and dynamic verification. Today, he's going to be telling us about probabilistic hyperproperties of MDPs. Very interested to hear your talk. Go ahead, Bernd.
All right, Danielle, thank you very much for the kind introduction. Thanks for having me. And by the way, thanks for organizing this workshop. I have to tell you, it's a delight to be here. I think this has been long overdue that we have something like this. So thanks for organizing this. So I'm going to talk about probabilistic hyperproperties. I know that this is a topic that many of you are interested in. I mean, the logic I'm going to talk about is PHL, which is the logic that Rainer, Hasem, and I came up with. There are other proposals around. For example, Bozo has been working on hyper PCTL. But I think in general, many people are realizing that we need to get probabilities in there. So let me start with the really big picture. So it has been a little bit more than a decade now since the seminal paper by Clarkson and Schneider, where they coined the term hyperproperties. And I think what has happened in the time since then is that we have gone from this semantic kind of definition to a detailed collection of logics that allow us to precisely express the properties we're interested in. So Clarkson and Schneider, of course, said that trace properties are sets of traces, hyperproperties are sets of traces. So this is easy enough. But then once you start looking at the logics for hyperproperties, you realize that, well, there's a whole hierarchy here. And not all hyperproperties are created the same. And depending on what types, in particular, of quantification you allow in your logic, you get very different powers of expressiveness. So this ranges from popular and simple hyperproperties like noninterference all the way up to fairly complex notions, say, of knowledge that all fall into this general category of hyperproperties that of course require very different logical tools. Now, probabilistic systems are kind of the obvious next frontier to tackle. I guess the main motivation really comes from the fact that many of our most important application domains have some sort of randomization in them. So, of course, in security, you have all sorts of privacy mechanisms that are based on randomization. If you look at mutex protocols, they do need some sort of symmetry breaking, and often that is done in a randomized way. Protocols use, network protocols use randomized waiting times, and in particular in cyber-physical systems, you often have uncertainty about the environment that manifests itself in randomized fault tolerance models, performance models, and the like. Now, the reason why this is so difficult and probably also why it's so interesting to look into this is that there's a profound change going on as we go from standard non-deterministic kind of systems to systems that have both non-determinism and probabilistic choice. And the key difference really is the mechanism with which non-determinism is resolved. So in a standard system, in a non-probabilistic system, the resolution of the non-determinism is determined by the execution path. And as a result, when we describe a hyperproperty, we relate multiple execution paths, right? Now, if you have a probabilistic system, then there is a feedback going on between the the outcomes of the probabilistic choices and the way the non-determinism is resolved. So the resolution of the non-determinism depends on preceding probabilistic choices. As a result, things are no longer so simple that you just need to look at paths, but rather this resolution mechanism is a strategy, the so-called scheduler, that based on the preceding probabilistic outcomes determines how to resolve the non-deterministic choices. So as a result, if you want to talk about hyperproperties of such systems, then really you need to relate multiple schedulers rather than just multiple paths. Now, let's again take a step back and talk a bit just about non-probabilistic systems before we make this happen in the logic for probabilistic systems. So in non-probabilistic systems, what we do with the hyperproperties is we relate multiple paths. So the classic example, of course, is noninterference, where we're worried about low security and high security inputs on the one side and low security and high security outputs on the other side. And we want to say that, well, the low security outputs should not depend on the high security inputs. So for example, we might say that the occurrence of the low security output success is independent of the values of the high security input. And the way this is done in logics like hyper LTL or hyper CTL star is that we introduce path variables, pi and pi1 and pi2, that gives us access to two different execution paths. And now we can relate those two paths by, in this case, saying that if they happen to agree on the low security inputs, then they should agree on the property over the high security outputs that we're interested in this example, that if we eventually reach the success on pi1, then we also need to eventually reach it on pi2 and vice versa. All right, so the mechanism by which we introduce the hyperproperty into a standard temporal logic is by introducing path variables. That way we can relate multiple paths. Now, back to the probabilistic hyperproperties. We already said a probabilistic hyperproperty needs to relate multiple schedulers. So, for example, we could say that the probability of eventually reaching success should be independent of the scheduler. Now, in order to express this in a logic, we need, in an analogy to what we just did in the non-probabilistic case, I'm sorry, we do need now variables that don't refer to paths, but rather refer to schedulers. So here we have a pair of schedular variables, sigma 1 and sigma 2. And now we use a PCTL style probability operator to say that, okay, if you run your system with scheduler sigma 1, then the probability of eventually reaching success is the same as if you run the system with scheduler sigma 2 and you look for eventually reaching success. Okay, so going from non-probabilistic to probabilistic systems, what we do is we introduce schedular variables rather than path variables. That sounds easy enough. But then you may want to actually not compare all sorts of schedulers, but maybe only ones that have that satisfy certain conditions. So, for example, here our scheduler might provide some inputs that are critical, others that are not, right? So what we might want to say is that the probability of eventually reaching success is actually independent of the secrets provided by the scheduler. The scheduler may well provide other information that is not secret, and then the probability of reaching success might well depend on that, but it should be independent of certain secrets. Now, in the non-probabilistic case, we said, okay, let's look at pairs of paths that agree on on the low security inputs to express something like this. So we need a similar mechanism now to relate schedulers. So the way this looks like here is that we again have our condition that the probability of reaching success is the same for the two schedulers. And we start out with a quantification over all pairs of schedulers sigma 1, sigma 2. But then in the middle, we have this condition that restricts the pairs of schedulers to such that actually satisfy a certain relationship. Now, in our case, that relationship is that they should agree on the low security inputs. Now, the somewhat tricky part is that we want to say that the schedulers agree on the low security inputs, but we don't have paths anymore that we could access as before with an LTL formula. Rather, we have schedulers, that is, we have infinite trees. So what's going on in here is that in this part that restricts the relationship between the two schedulers, we introduce path variables again. So the path variables allow us to talk about the paths in the strategy. And then when we have selected a pair of such paths, pi1 and pi2, so pi1 comes from the first scheduler, pi2 comes from the second scheduler, and then we have paths that we can actually work on with an LTL style formula. So in this case, we say that it's globally the case that the low security inputs are the same. So you see how inside our new logic, we find again the hyper LTL core that is needed in order to express a relationship between multiple schedulers. All right. So what we have here is a logic that has both quantification over schedulers in order to compare the different situations, and we have a quantification over paths in order to compare the schedulers themselves. And we call this logic PHL, Probabilistic Hyper Logic. Now, let me give you a few examples, what you can do with that. The first example concerns a model of two robots that work in a warehouse. And we want to say that the plan that one robot has is robust against interference by the actions of the other robot. Or more formally, for every plan of robot A, the effect of the plan of robot B on the probability of robot A reaching its goal is bounded. So here you see a simple arena and the two robots, right? And they both try to get to the goal, and the different the robots can take different actions, and then their effect on how they move on the arena is probabilistic. And the property says that robot B can only do limited harm. So if robot A has a plan, then the probability of that plan succeeding may be affected by whatever robot B does, but only to a limited extent. So this is a PHL formula that expresses that. So we have, again, a quantification over two scalars. And the scalars now always describe the moves of both robots. And what we want to say is that we're comparing two different situations where robot B may behave in a different way, but robot A executes the same moves. So we're comparing what happens for a specific plan of robot A in two situations, which may be different in terms of what robot B does. So we can see what the difference in the actions of robot B has on the probability of success for robot A. Okay, so we have this this condition that says that if we look at two paths in the two schedulers, then it's always the case that the moves that robot A selects are the same. The only difference is in the moves of robot B. Okay, and if we have two such schedulers, then we again do this comparison in terms of probabilities. So we say, okay, we compute the probability that robot A reaches the goal in situation sigma 1, and compare that to the probability of robot A reaching the goal in situation sigma 2, and the difference of these probabilities should be bounded by some epsilon. Okay. The second example here is a property where we look at the effect certain actions have on the probability of an effect happening. So in this example, we're driving on a country road. So this car here, that's us. And what we're saying is that if we decide to enter the opposite lane when there is oncoming traffic is a bad idea, in the sense that if we do that, then this will increase our likelihood of having an accident. Okay, so the general pattern is that executed a certain action B when there is a condition P, in this case, a car is approaching from the opposite direction, right? This will increase the probability of a certain effect, in this case, an accident. Okay, so in the formula, we're interested in a pair of situations. So sigma 1 and sigma 2 describe two alternative behaviors of the same car, of us, where sigma 1 is our safety conscious self, where we don't switch the road, and sigma 2 is the more adventurous self, where we switch to the other lane despite there being oncoming traffic. Okay, so it's again this pattern that we need a condition that restricts what situations we want to compare, because we don't want arbitrary comparisons, but only specific ones. And in this case, we first of all say that the action B is never taken when the condition P is satisfied. So this is on path pi 1, which is an arbitrary path from our safety conscious scheduler sigma 1, right? And so on all such paths from sigma 1, it's the case that we never take action B, that is, we never switch to the opposite lane, even though we're in condition P, that is, there is traffic in the opposite direction. So this ensures that sigma 1 is actually a safety conscious scheduler. Now, this condition C here says under what circumstances do sigma 1 and sigma 2 differ, right? So they should not be arbitrarily far apart, but rather sigma 1 and sigma 2 should only differ when sigma 2 actually takes action B despite P being satisfied. So as long as there is no oncoming traffic, the two cars, let's say drivers, the two schedulers do the same thing, right? But if there is oncoming traffic, then we allow sigma 2 to actually do something more dangerous, that is switch the lane, right? So this is expressed as this wait for formula that is released when there is an actual difference in the outcome of the probabilistic choices. And until that happens, we require sigma 2 to take the exact same actions as sigma 1, unless we are in a situation where we want sigma 2 to be more adventurous, namely where there's oncoming traffic and the path pi 2, that is the execution of sigma 2, decides to switch to the other lane. Okay. So we have described the behavior of sigma 1, and we have described the relationship between sigma 1 and sigma 2. So the only thing left to specify is the desired outcome, namely that the probability of eventually reaching an accident should be strictly higher in scheduler sigma 2 than in the safety conscious scheduler sigma 1. Okay, so with all that, let me quickly give you the full picture of the logic. So at the high level, we have a Boolean combination of quantified formulas. So here we have the quantification over the sigma, that is over the strategies. Then below that, there can again be Boolean combinations, and these are built on two types of subformulas. So these are the probabilistic predicates and hyper-CTL star subformulas. So the probabilistic predicates express that there is some threshold on the probabilities. So what we do here is we build a linear combination of probabilities where individual probabilities are computed by this standard probability operator. So this is P of phi, where phi is an LTL formula, and this describes the temporal behavior that we want to measure. The only noteworthy part here is that atomic propositions are indexed by a specific scheduler. So we can say that the probability of some temporal property being true for a particular scheduler has a certain value, right? And then we can combine multiple such probabilities in a linear expression and finally compare it to a threshold. Okay, the other subformula is the hyper-CTL star subformula. So here we quantify over paths, and the quantification over paths always refers to a specific scheduler. So we say that we want a path from a particular scheduler, and then we essentially have the full power of hyper-CTL star in order to express this hyperproperty over one or multiple schedulers, just as we wish. Okay, so this is the logic. Now, quickly, how do you evaluate such formulas? Let me give you an example where we don't have a hyper-CTL star formula in there first. On the next slide, we have it in there. But just to keep it simple, so in this example, we have an MDP, right, with two actions, H and H bar. And this is a really simple example. We start out in this yellow initial state as 0. And for our two actions, H and H bar, there's a certain probability that they will lead to a green state. And there's a certain probability that they'll just stay in the initial yellow state. And now we have a PHL property that says that for all pairs of schedulers, the difference in probability of reaching green in the next step is bounded by 0.1. Okay, so let's say what we need to do. So we need to check this for all possible assignments to our universally quantified scalar variables. So let's say we have an assignment that assigns a particular scheduler to sigma 1 and sigma 2. And then we need to check this probabilistic predicate. And in order to do so, we consider a particular Markov chain. So the way we built this Markov chain is that we first of all build the self-composition of the MDP in order to account for the two scenarios in parallel. And then we apply the combination of the two schedulers to this self-composed MDP. When you do that, then you turn the MDP into a Markov chain, so no non-determinism is left. And then we can simply check that this probabilistic expression is true for the resulting Markov chain. Okay, so now let's go to a slightly more tricky example where we do have such a hyper-CTL star formula in there. So this property says that every two schedulers that agree on the low inputs have the same probability of eventually reaching a green state. So in this MDP, we have four actions. There is LL bar H and H bar, the intuition being that L is the low security input, H is the high security input. And what you can see is that if we move with L hat, then we get to a green state, right? And if we move with L, then we always go to a red state, no matter where we are. So, if we want to say that the low security inputs are always the same, then we can simply express that by saying, well, we're always in the red state at the same time, right? Because if we have L hat, then we go to green. If we have L, then we go to red. So if we have red exactly at the same positions, then that means that the low security input has been the same. And this is actually what happens in this formula. It says that on all pairs of paths from our two schedulers, the red state is reached at the exact same time. Okay, so for all schedulers that have this property, we want to say that the probability of reaching a green state is the same. Okay, now the procedure is pretty much the same as in the previous example. So we do the self-composition of the MDPs, we apply the schedulers to the self-composed MDP, we get a Markov chain, and on that Markov chain, we can compute the probabilities and make sure that they are actually the same. Now, the only thing left to answer is how do we evaluate this hyperCTL star formula? Because obviously that needs a transition system, not a Markov chain. And the way we do that is simply that we build a transition system from this Markov chain that results from the self-composition of the MDP with the schedulers applied, right? And we simply ignore the probabilities. So we just look at the transition structure that results from applying the schedulers. Okay. Now, let me just quickly say that PHL, of course, is in a great company as far as logics go. I mentioned initially Borzo's pioneering work on HyperPCTL and HyperPCTL star. So these were logics that quantify over the states of a Markov chain. So at this early stage, these were Markov chains, not MDPs. Then there are a number of logics that have this idea of combining quantification over strategies and having some sort of probability operators. So stochastic game logic is an example for that. And probabilistic strategy logic is actually very close in the sense that you can quantify over strategies and then compare probabilities. And finally, there is HyperPCTL for MDPs. So this is the same logic as up here, except that now we're interpreting the logic over MDPs. But we still have these mechanisms of, for MDPs, quantifying over schedulers, and additionally quantifying over state. So in all brevity, I think the key difference between these logics and PHL is that they don't have this mechanism of quantifying over paths. And of course, quantifying over paths is kind of essential when you deal with reactive systems, because you don't just have a one-off input, as in selecting a different initial state or so, but rather the input comes in an infinite sequence. And if you want to capture that, then you do need the ability to compare different paths of the schedulers. All right. Now, sadly, the model checking problem for PHL is undecidable. This is sort of a natural consequence of its expressive power. And one easy way to see that is that the emptiness problem for probabilistic Büchi automata, which is known to be undecidable, can be encoded very easily. So the way you do that is you construct an MDP and a PHL formulas such that the probability of an that there is an input word W with a probability greater than 0 if and only if the MDP satisfies the specification. And the way you do that is you let the scheduler pick the letters and in this way generate the word. And then the probabilistic choices mimic what the Behe automaton would do. So in that way, you get a PHL formula that says there exists a scheduler representing the input word to the automaton, and the hyper CTL star constraint simply makes sure that your scheduler actually encodes a word that is on all paths sigma. You find the same letter, so it actually encodes one single word, and then the probabilistic predicate just makes sure that the acceptance condition is true. That is, the probability of infinitely often visiting an accepting state is greater than 0. Another easy way to see that the model checking problem in general is undecidable, and this is actually a very interesting point of view, is that the synthesis problem for hyper LTL can be encoded in PHL. And I mean, this is an absolutely trivial observation. If you want to say that hyper LTL formula he is realizable, then you simply say in PHL that there is a scheduler that has this property. So you can directly say that. But of course, we know that the synthesis problem for hyper LTL is a really, really hard problem. In hyper LTL, you can express the synthesis of distributed systems because you can encode any sort of architecture by just saying which process is allowed to depend on which information. And since distributed synthesis, of course, is undecidable, so is the synthesis problem for hyper LTL. In fact, we know that there is only a very small fragment of hyper LTL for which the synthesis problem is decidable. This is the linear universal fragment, plus some not very interesting fragments like the existential fragment. So the big chunk of interesting formulas is undecidable. Now, on the other hand, of course, we know that we can do synthesis for hyper LTL. We just can't solve the general realizability problem, but the bounded synthesis problem, which asks if there is a solution up to a given number of states, that can be done. And in fact, this is implemented in Bose Hyper. So this is, of course, also what we'll make use of in PHL, that while the synthesis problem in general is undecidable, there is this core, and really the one that we're interested in from a practical point of view, where we build small solutions. Okay, so back to PHL. The general model checking problem is, as we said, undecidable. An almost trivial observation is that if we introduce this bound B and we restrict the interpretation of our scheduler quantifiers to just deterministic finite memory schedulers, then this is decidable. We can just enumerate all the schedulers up to a given bound and then make sure that the rest of the formula is true. So we won't stop at this point, but rather what we do in the following is we look at a fragment of PHL that follows the pattern that you have seen in all examples so far. The reason we're not jumping on this idea of looking for finite state or bounded size schedulers is that this would, of course, change the semantics of the logic, which we don't want to do, but we'll use it in a moment in the algorithms. So the pattern that we're interested in are formulas where you have universal quantification over schedulers. Then you have a constraint that restricts the schedulers, and then you have your probabilistic predicate. And the restriction here is in the hyper-CTL star formula that's allowed as a constraint. So the formula comes from the universal fragment of hyper-LTL. We only allow one path quantifier per scheduler variable. That is, you only refer to with one path to each scheduler, not with two paths to some scheduler. And we restrict the whole thing to hyper safety. So with this restriction, the problem is still undecidable, but now we can give two algorithms that approximate the problem from two sides. So first of all, we do an approximative model checking for formulas of this form that over-approximate the set of allowed tuples of schedulers. So we try to prove the property for a larger set of tuples of schedulers. If that succeeds, then it also holds for the particular set of tuples that we wish to consider. And we have a second algorithm that looks at the dual formula. That is, we look at for a tuple of schedulers such that the negation of the formula is true. So we look for counterexamples. And here we under-approximate the tuples by looking at only schedulers of bounded size. So by having those two procedures, we can prove and we can disprove properties, and this means we can approximate from both sides. Okay, so let me quickly give you the idea of the two algorithms. So in the approximative model checking, so we have to solve this universally quantified formula, which means that we have to see if for all n tuples of the schedulers in our MDP, the probabilistic predicate this here must hold for all schedulers that actually satisfy the n-safety hyperproperty expressed here. Now, what we do is, instead of actually checking all n tuples of schedulers, we build the n-fold self-composition of the MDP and then look at all the schedulers of this self-composed MDP. Now, at this point, we actually do an approximation because this scheduler for the composed MDP has access to more information than the individual schedulers would have. It actually sees the state of all the other individual schedulers, right? So we make this scheduler more powerful than the individual schedulers would have been. As a result, it's not always possible to take this scheduler for the self-composed MDP and translate it back into a tuple of schedulers. So we of course greatly simplify the problem by going to this big scheduler, and then we encode the n-safety hyperproperty as a deterministic safety automaton, and we check the probabilistic predicate on the such combined MDP. So in a little bit more detail, we have our formula here and our MDP here. What we do first is we build the self-composition of the MDP simply by looking at how many quantifiers there are and building the corresponding self-composition. Then we take the Hyper-LTL formula and translate this into a safety automaton. These two things then get combined into this big MDP. At the same time, we look at all the LTL formulas in the probabilistic predicates and translate them into Rabin automata and combine that with the big MDP. And then we look for optimal solutions to our linear expressions. And this optimal solution computed by a linear program is then compared against the threshold. Okay. Now, if that succeeds, then we know that even for a superset of the schedulers, our property is safe. Therefore, it does hold also for any real tuple of schedulers. Now, if that's not the case, then we don't know what's going on. And in this case, we look for a counterexample. So in the search for a counterexample, we need to search for schedulers that satisfy the Hyper-LTL formula and that additionally satisfy the probabilistic constraint. Remember, this formula is the dual of the original formula because we're looking for a counterexample. Now, what we do here, of course, is we replace the search for arbitrary schedulers with the search for schedulers, deterministic schedulers of bounded size. That we do with bounded synthesis for Hyper-LTL formulas. And for every solution to this, we then have an MDP, and we can check, we have a Markov chain, and we can check that this Markov chain satisfies the probabilistic constraint. All right, so here the workflow is first we construct a consistency constraint that ensures that the schedulers can be decomposed. The combined scheduler can be decomposed into a tuple of schedulers. We combine this hyper-LTL constraint with the hyper-LTL formula that we're given, that we give to the hyper-LTL bounded synthesis procedure. And here we enter this synthesis verification loop where we generate a scheduler, apply the scheduler to the self-composition of the MDPs. That gives us the Markov chain, which we check with model checking. And if we succeed, well, then we have a counterexample. If not, then we add a constraint that excludes that scheduler from further consideration, and we try with the next scheduler. Okay, now I don't want to spend much time because I'm running low on time on our experimental results, but let me just mention that, of course, there's an interesting question going on. We're doing synthesis and we're doing verification. So which of the two parts actually contributes to the complexity of the whole thing? And the answer is very clear. It's the synthesis. So what you see here, this is the synthesis time as we go to growing arenas. So this is the robot example where the robot runs through arenas, and we're looking at larger and larger arenas. And of course, the synthesis time grows very rapidly, versus the model checking time is, by comparison, almost negligible, right? So what we see here is that, of course, this is hard because it contains the really hard synthesis problem as a subproblem. And our technology for synthesis is at this point there, but not really satisfactory. And this is what we see in the running times. On the other hand, of course, synthesis is really, really interesting in its own right. And any advance in synthesis will immediately cut down on the bulk of the running time needed for the PHL model checking. So to summarize, we've looked at this logic PHL, which combines quantification over schedulers with quantification over paths. It sort of has the best of both worlds from logics like hyperctl star and probabilistic logics. It's a really powerful logic. And therefore, it's not surprising that the general model checking problem is undecidable, but we have this approximation from both sides. So that's very promising. In terms of actual practical results, we notice that synthesis is the really hard problem. So before one can turn this into something that really works in practice, one needs a practical synthesis algorithm. For now, this works really well as long as the state space is not too large. But of course, as soon as we get to strategies with a significant number of states, just as in synthesis, this can get very tricky. So thank you very much for your attention, and I hope we still have a little bit of time for a few questions.
Yes, thanks, Bernd. We have time for a few questions. So while people are thinking, I want to start out with a quick question. You mentioned that in the bounded synthesis algorithm, you're searching over, if I understood correctly, deterministic finite memory schedulers. But it seems like for some properties, you might need probabilistic schedulers. I'm thinking of something like a Nash equilibrium type of thing, where maybe if you like the specification you showed, where one robot should not be able to interfere much with the other, right? It might be that that's only achievable by some kind of mixed strategy or something like that. So is it sufficient to just search over deterministic schedulers? And if so, could you give some intuition for why that's the case?
So, what's going on in here is really that we're using what we're having, right? So we have a synthesis procedure that gives us a deterministic strategy, and the whole problem, of course, is undecidable. So you cannot even say that what would be sufficient for that. I guess this is something to play with as we have more powerful synthesis available.
I guess, but in the examples that you had in the experiments you were doing, it was generally possible for those types of specifications anyway to find deterministic schedulers.
Yeah, that's certainly true. I mean, maybe Rainer, you want to comment on that. I'm pretty sure there's a completeness result in that direction, right?
I mean, they're very simple, because you have this quantification over the paths, right? So there is a very simple example where you need randomization, right? If you only have kind of two actions, and then every deterministic scheduler will choose one of them and, let's say, satisfy or not satisfy certain proposition, and your property is asking that there exists two paths, one that satisfies the proposition, another one that doesn't. So you do need for the existential case, when you have existential quantification over the paths, you do need randomization. And in the examples that we had, because the property negates it, so essentially it's it's unrealizable, and there we had deterministic schedulers, but that suffices. But otherwise, in general, not.
Yeah. Yes. But I think this is great because that just gives another motivation to study all these fun synthesis problems, because here we have another application for those.
Right. Borzu, any questions?
Hi, Bernd. Thanks a lot for the talk. So I agree with all the things that you said in the previous slide, right before conclusion, about where the complexity of the problem is, which is in synthesis. So we have also experienced exactly the same things, in HyperPCTL. The general model checking problem is undecidable exactly for the same reason, because of undecidability of the emptiness problem in probabilistic Buki automata. So, and now we are working on introducing rewards for performance analysis, which makes the problem even more horrible in terms of scalability. I mean, we cannot go beyond a couple hundred states for verification with rewards. So one way to look at it is, what you said, where so we wait for better synthesis algorithms that will help, and I agree. Do you have any other thoughts on how to tackle scalability? Because that seems to be the main problem here in both approaches of PHL and HyperPCTL. So we need, something probably out of the box, some breakthroughs that can tackle the complexity. Do you have any other thoughts other than let's wait for better synthesis algorithms?
No, I think the synthesis problem is at the heart of this, and there is no magic trick that will get it out there, because this is exactly the problem we're trying to solve. So I think, I would say, be careful stacking even more complexity on this, and let's look at the core issue. So I think maybe one point to be careful about is the scalability is really limited by the size of the scheduler strategy. It's not limited by the result of the resulting verification problem. That scales really well.
Yeah.
So as long as the scheduler needs very little memory, you're completely fine. And of course, we know that in practice, often the scheduler doesn't need all that much memory. Now, I think this is an inherent issue with synthesis, that we need to figure out at which points do we get the most bang for the buck in terms of strategic memory, right? So compositional methods and all this can help to make this scale to larger things. But in the end, this is the inherent metric of the hardness of the problem. How much state do you need in the strategy? So, my intuition is there is no way of getting around this, because this is inherently in the problem. But of course, right now we're extremely wasteful in handling this. Essentially, we're pushing this into the constraint solver, and the constraint solver knows very little about our problem, so it is way too slow as compared to what it could potentially be.
Yeah, we've observed exactly the same things, that when it comes down to DTMCs, it is there are also these numerical methods for verification of DTMCs, which are very efficient. You can go all the way to millions of states. But then the initial step, which is the scheduler quantification, which is killing everything. But yeah, I agree with all the things that you said.
Well, I guess all this, Borzo, was a big teaser for your talk in a little bit later in this workshop, right? Because you'll explain to us how to do better synthesis.
But that's controller synthesis. That's easier than this. Yeah.
All right. Thanks for the question, Borzo. Let's keep going. We've got one more talk.